Hello everyone, Ms. Saturian here. So we are on our first video of this new unit. It covers atoms, subatomic particles, conductors, and insulators. The essential question for this video is, what are subatomic particles and how do they behave in different materials? Some of this material in the video may be familiar to you from middle school science, so you can go through this video pretty quickly. But if it isn't, really take your time to get a good understanding about these topics, as they will be really important in understanding the topics that we'll cover in this unit. So let's start small. Atoms are the building blocks of matter. If you zoom in on anything that you're looking at, the closer you get, the chunkier it gets. Take, for example, this ant. If you zoom in even more, you see more parts of that ant. And if you zoom in even more, you'll eventually get to the atoms that make up that ant that look almost like little Lego pieces. There are currently 115 types of atoms that are known as the elements that we can find on our periodic table. So for the longest time, scientists thought that the atom was the smallest particle that exists. But as time has gone by, scientists have discovered that there are even smaller particles that make up atoms called subatomic particles. Each atom is made up of subatomic particles called protons, neutrons, and electrons. Here's an example of a classical view of the atom, but it is generally much more complicated than what this picture shows. That's something you'll learn about when you take chemistry next year, but the basics of this picture hold true. There's a tiny and dense area right in the middle that holds both protons and neutrons. This whole area is called the nucleus. The electrons whiz around the outside of the nucleus along something called orbitals, as if they orbit around the nucleus. This is the area of the atom that holds a lot of the volume of the atom, so it takes up a lot of the space in an atom. Each of these subatomic particles has a mass and some type of charge. So in this class, the two subatomic particles we will be paying the most attention to are protons and electrons. Both protons and electrons have pretty unique characteristics, which is what I'll be sharing with you on this slide. So let's start with protons. They have a lot of mass and are almost always stuck in the nucleus, or that centermost part of the atom. It also has a positive charge. Electrons, on the other hand, have a really small mass and orbit freely around the nucleus and can even move freely from one atom to another. They also have a negative charge. So when we talk about the movement of subatomic particles in this unit, we're really talking about those electrons, because if protons were to move out of the nucleus, what happens is known as nuclear fission, or you can think of it as a nuclear explosion. And we don't want to have those types of reactions in our physics class. As I mentioned before, most of the mass in an atom is found in the protons and within that nucleus. So you could say that most of the mass in the human body comes from protons. The charge of both protons and electrons determines how they interact with one another. Charge is kind of like mass because it's a conserved property, just like mass. It is the reason why we have electric forces and electricity. So charge is a new variable we can measure when talking about electricity. The unit we use to describe charge is a coulomb, or that capital C that you see on those bullet points over there. Each proton has a positive charge, or 1 plus C, or coulomb, while each electron has a negative charge, or minus 1 C. When you bring a proton and electron together, or two protons and two electrons together, there's a force that they experience from each other. The direction of that force depends on whether those charges are positive or negative. So when you have a positively charged proton and negatively charged electron, and they come close to each other, the charges attract with one another. On the other hand, when you have two negatively charged electrons with negative charges coming closer together, they repel from one another. The same thing would happen if two positively charged protons were to come close to one another. So in this sense, you can kind of think that opposite charges attract, and then like charges repel from one another. The electrostatic force is the strength of the force that attracts or repels objects that are charged. So, along with gravitational force, the electrostatic force is one of the four fundamental forces in our universe. So, it's kind of a big deal. All the other all the other forces that we've learned about, like friction force or like normal force, tension, spring, those are all actually electrostatic forces. The strength of this electric force has a linear relationship with the amount of sigma, or total charge, of each object. So the larger the total charge of each object, the stronger the electric force. The strength of the electric force also has an inverse relationship with the distance between them. So the smaller distance between them, the larger the strength of the electric force, where they would be attracting or repelling one another. One process that has to do with the behavior of electrons is polarization. This is something that you may have noticed that's actually a pretty big deal in the real world. Polarization is something that happens when you have an object with a positive or negative sigma, or total charge, and you are getting it close to other objects. A good example of this would be like when you're getting your sock out of the dryer and it sticks to you. That's actually polarization at work. The sock has a charge. You, as that person, are neutral, and it still wants to stick to you. The reason for that, again, is polarization. So what happens when you have that object, like the sock, out of the dryer that has a really big charge and you put it near a neutral object? In this left diagram, you have an object with a really large negative charge, like the sock from the dryer. There is a really large unbalanced charge there, with lots of negatively charged electrons and only 4 positively charged protons. On the right, you'll see a diagram signifying the neutral object, like yourself wanting to get the sock out of the dryer. Right now, there are only 4 protons on there, but if I add my 4 electrons to make that object neutral, you'll notice that they're not randomly distributed in that object. They actually move far away from the electrons on the left, or in the left diagram. Remember, like charges repel each other. Since the whole other object is negatively charged, the negatively charged particles in the other object on the right want to naturally repel and move away. The protons can't move because they're stuck in that nucleus. So this object on the right is still neutral, since the proton and electron charges balance out. So it's +4, -4. Let's see. We're neutral, but we have these 2 poles. The result of this is 2 different forces. We have an electric force pushing to the right from the electrons that are being repelled, and we have an electric force being pulled to the left from the protons on the left half, being attracted to all those electrons from the object on the left. So the object has 2 forces acting on it, repulsive and attractive. Remember, think of the left diagram as a model of a sock in a dryer with lots of negative charge, and the diagram on the right as you, that person, a neutrally charged object trying to pull the sock out of the dryer. Even though we are a neutral object, we can still experience electric forces, because if you zoom inside that object, we have little tiny charged like particles. The electrically charged sock was really attracted to your body, which is why it wants to stick to you. Polarization always leads to attraction, because even though we have the same number of electrons and protons on each half, that positive half is a lot closer to the negative object than the negative half. Since that half is closer and the electric force depends on distance, then that pulling attractive force ends up being a stronger force than the repelling force. So overall, the sigma, or total force, the unbalanced force, ends up being attractive when you have an object that's being polarized. The world around us is full of protons and electrons, making up all the materials around us that we interact with each day. Some materials respond differently to electricity than others. You can kind of categorize these objects into two different categories called conductors and insulators, words that may be familiar to you. Protons are stuck in the nucleus. Because of this, the number of protons in an atom stay constant. This number actually determines which element the atom is and gives it those physical properties that that atom has. One of those physical properties is actually electric conductivity. Conductivity is how easy or difficult it is for electrons to move from one atom to another. So certain elements have high conductivity while others don't. One category of materials is known as insulators, which is a material with low conductivity. This means that the electrons do not move easily from one atom to another. Another way you can think of this is something that you can safely stick into a light socket without electrocuting yourself. There are high energy electrons in that light socket, so if you stick an insulator in there, those electrons can't move out to basically electrocute you. When parents don't want their little babies sticking things into a socket because they don't know better, they use a plastic cover to put into the socket for this reason, because plastics are good insulators. So the reason that electrons don't move very easily inside of insulators is because the nuclei of the atoms hang on super tightly to those electrons. Just a side note, nuclei is the plural of nucleus. Insulators, or in insulators, electrons move around inside the atom, but it's not easy for those electrons to escape. If you could zoom in on an insulator, you'll notice that the protons and neutrons come in matched pairs. So those plus signs are the protons, the minus signs are the electrons, and you can kind of think of this scenario like Velcro. Both sides want to basically stick together. Some good examples of insulating materials I've got down here are wood, rubber, plastic. And so now let's kind of move on to conductors, which is the opposite of this. The type of material that has a high conductivity is known as a conductor, where the electrons can move easily around the atoms from one atom to the next. Another way you can think of this is something you shouldn't stick into a light socket because you would electrocute yourself. There are high energy electrons in that light socket again that could easily come out and cause electrocution. Something like a metal fork would not be a good thing to stick into a light socket because that one's a good conductor. So the reason that electrons do move very easily inside of conductors is because the atoms are happy to share their electrons. The electrons can move anywhere in the material and can easily move on or off the material and onto another conductor as well. So if you touch conductors together, they will happily share electrons. Now, if you could zoom in on a conductor, you'll notice that the protons and neutrons are still neutral, but it looks a little different. So we've got an equal amount of pluses and minuses. The electrons here can go wherever they want. You can't count on all of them being close to their protons. Some could be, some not. A couple of good examples of conductors are metal and water, as those two things allow for electrons to move freely throughout them. All right, we're done. Let's revisit this essential question. What are subatomic particles and how do they behave in different materials? I hope you enjoyed this. Now get on to your next video. Adios.